Entonces, ¿estamos listos, Diego, con la transmisión en línea?
Dame un segundo, profesor. Listo, sí, ahí dice que ya estamos transmitiendo.
Perfecto, pues entonces, muy buenos días para todas y todos. Muchísimas gracias por estar nuevamente conectados aquí. Estamos en línea ya transmitiendo por YouTube y por Zoom. eh, en lo que va a ser nuestra tercera sesión en línea de la EIFA 2024, herramientas de inteligencia artificial para las ciencias naturales. Es un gran placer para nosotros nuevamente podernos volver a reunir y pues espero que las dos sesiones que llevamos hasta el momento y por supuesto las tres en línea que faltan, pues sean del agrado y pues les ayuden ustedes a fortalecer mucho más los conocimientos en esta área tan interesante del conocimiento. De hecho, pues si bien ustedes ya tuvieron la posibilidad de ver los premios Nobel de esta semana, específicamente el premio Nobel en física fue otorgado a dos científicos estadounidenses, que uno de ellos prácticamente pues dio las bases para el desarrollo de las redes neuronales y aplicó estos conocimientos en el ejercicio digamos, en su ejercicio en el contexto de la física. Entonces, estamos en un momento bastante importante, digamos, de la humanidad en términos del desarrollo de las capacidades que tienen estos sistemas de inteligencia artificial, y entonces eso claramente demuestra la pertinencia que tiene esta escuela. Eh, pues tenía pensado hacer la presentación en inglés del profesor Morten, pero creo que para no perder el tono de la introducción, pues voy a permitirme hacerla en español, no obstante, sin pues indicar que la charla, la escuela que vamos a tener hoy, pues va a ser desarrollada en inglés. El profe afortunadamente entiende mucho de lo que estamos diciendo ahora, tiene un español bastante bueno, afortunadamente, entonces, pues entenderá muy bien esta primera parte que estamos comentando, pero después cambiaremos a inglés para que se sienta mucho más cómodo en su presentación. Entonces, específicamente, pues es de verdad un placer para mí poder presentarles a ustedes al profesor Morten Hjorth-Jensen. Él es profesor de la Universidad del Estado de Michigan y también de la Universidad de Oslo. Él tiene una carrera impresionante, es extraordinaria como físico teórico, en ciencia de la computación y en la teoría de muchos cuerpos. Específicamente su trabajo ha estado concentrado en problemas de la estructura nuclear y pues ha utilizado muchos métodos para resolver las ecuaciones de Dirac y de Schrödinger en estos contextos, utilizando inclusive herramientas de aprendizaje automático para estos sistemas que son sistemas de muchas partículas interactuantes. Eh, la verdad, el trabajo del profesor Morten es impresionante y básicamente pues estoy muy emocionado de tenerlo acá porque el profesor Morten, desde el primer día que le propusimos la escuela, eh, pues dio su apoyo completamente a la misma y creemos que ese conocimiento que tiene de Machine Learning, digamos de aprendizaje automático y de computación aplicado, por ejemplo, a la cuántica, pues le dan a esta escuela pues una dimensión enorme. Y pues no tengo duda pues que todos aquí pues vamos a sacar muy buena ventaja de ese conocimiento. Entonces pues agradezco mucho la disposición del profesor Morten por estar aquí, por compartirnos su conocimiento y pues la verdad tenemos mucha suerte de tenerlo acá. Esperemos que así como me siento yo emocionado por tenerlo acá, pues todos ustedes también al final de la sesión se sientan inspirados por todo esto que él nos va a presentar y por favor les pido con las reacciones del Zoom un fuerte aplauso y deditos arriba para darle la bienvenida al profesor Morten. So, Morten is your audience, so please go ahead.
Y mil gracias, Omar, mil gracias por tu introducción. Es muy impresionante, ¿eh? Y bienvenido a todos, buenos días. Que yo, el mío español es una mezcla de italiano y un español inventado. and then I will speak, I will go over to English. I hope my English is clear enough. It tends also, since Italian is my first language, it tends to be very Latinized. So I hope you will get my message. By the way, I just wanted to say one thing, because there is a comment in the chat here. El premio Nobel per la química también fue por el aprendimiento automático, machine learning. And this is quite impressive, because you have two of the big Nobel Prizes where you had foreign Nobel Prize winners who actually dedicated most of their life to machine learning.
Mhm.
So this is impressive, actually. It's a good time to actually start with this. Now, there's one thing which I was wondering, I mean, you guys don't need to answer this now, but I assume that many of you have probably studied some machine learning methods, and probably somebody here has actually already written a code for neural networks. It's not unlikely. So I'm trying to find a kind of level which is going to probably find a middle way, so that some of you may not have seen these things before. And then hopefully you can see the basic steps in setting up a code for a neural network.
Well, Morten,
Yeah.
excuse me. Fortunately, in the previous session, we were discussing about this first step for introduce the people here in the school for those tools for machine learning, even including neural networks. So they had been working a little bit in this.
So guys, I mean, feel free to put questions in the chat as we move on, and we will try to answer them as we go on. And I would also, Omar, if it's okay, if we take a small break after something like 45, 50 minutes, because else I'm going to put all you guys asleep.
Okay, nice. Good, nice.
So, is it okay if I share the screen? So let's just do that. And can everybody see my screen now? Is that functioning?
Yes.
Perfecto. Bueno, so what I wanted to give you today is an introduction to neural networks and deep learning. So the name deep learning comes from the fact that a neural network consists of input layers, and there are hidden layers, and you can have as many hidden layers as you want in the training of a specific model, which means that the deeper it is, then clearly the more variables you will have to train, the more parameters you will need to optimize in order to fit a specific function. So my aim here is to give you the basic building blocks so you can build your own neural network code. Now, we will not have time to go through everything today, unfortunately. So if you scroll down through this Jupyter notebook, and everybody should have access to these Jupyter notebooks now. So if you don't have access, just please send me a mail. I think Omar put the link online, and then you can take my, it's actually in my GitHub address, and you will find and actually for those who do not have it, let me just set this up immediately for you in the chat. So I'm going to put up the link in the chat for you guys. So let me just bring up this link, and then you can, when you have this link here, this is where I will place all the teaching material. So let me just put that one in here. So you have it in the chat. And yeah, Omar already did it. Thanks, Omar. Sorry for that. Yeah. So I didn't see that. And here, if you move into the doc folder and you go into the first lecture, which is the one we're having today, you can find the notes which you were seeing either as a Jupyter notebook. This is where you have the Jupyter notebook, which I'm going to run now. Or if you prefer a PDF format or an HTML format, you can look it up here. So essentially, this is where you can find what I'm showing you here. Now, one thing which I have in the beginning here is some links, and later you will see also some links to textbooks, which are actually pretty good. So there are some videos here which are somewhat instructive. And we also have Michael Nielsen's approach to neural networks. And there is a set of lecture notes, which is actually excellent. Below, I'm also linking to a textbook, which you will find very useful, actually. So the introduction to the neural networks, which I'm going to give you now, is going to be a little bit back and forth. So we got the Nobel Prize in physics and also in chemistry, which is based on many of these deep learning methods. The idea now is to give you a basic overview of what are the essential ingredients when you're going to develop your own code. I'm going to present to you some simpler examples. And then below here in this Jupyter notebook, we will not have the time to go through that today, but this is something which we will pick up again when we meet in person in Cali. And then we will discuss that part. Then after we are done with the setup of a neural network code, we are going to use that one to solve differential equations. And this is actually one of the hot topics in, let's say, in applications of neural networks in the physical sciences. And we're going to look at the solution of ordinary differential equations and also partial differential equations. And at the end, we will start scratching the surface on something which is called physics-informed neural networks, which has become extremely popular and is widely used in solutions of complicated partial differential equations like the Navier-Stokes equations in fluid mechanics, or even the Schrödinger equations in quantum mechanics. So much of the naming of neurons comes from the fact that many of these models were inspired by developments in neuroscience. And these were terms which were coined back in the 40s during the Second World War. There are, in general, there are kind of four main categories. So we would typically have a general purpose neural networks for supervised learning. So the way we are going to look at it is actually as an application for supervised learning, which means that the input data and the output data are labeled. So you would typically have a data set like a data set on classifications of tumors. So you can have a tumor which is benign, and then you would give that an label 1 or true or false, whatever you want to choose. And then you have the other case where the tumor is not benign, a malignant tumor, and then you would give that a label 0 or true or whatever you prefer to label. That's a binary case, but all the data have been labeled. And then neural networks are often also used for specifically for image processing. So there's an extremely popular set of neural networks, which is called convolutional neural networks. And when we meet in person in Cali, for those of you who are interested, we could also digress and discuss some of these neural networks implementations. And then we have neural networks for sequential data. And if you're looking at time series, which is pretty common in the physical sciences, that you have some data, you may have some patients, and you measure the heartbeat of these patients over time. That would be an example of a time series. And then you would like to make a prediction on how this patient's heartbeat is going to develop over time. So you would train a network on that, on these data. So another thing which is extremely popular nowadays, and you will see that neural networks, one of the reasons why we focus on you understanding how we develop a neural network code and what is the machinery, is because neural networks function often as building blocks in these more complex deep learning methods. So like a convolutional neural networks, at the heart of it, there is a neural network, which is used for the training. And the same with recurrent neural networks. But also, if you look at Boltzmann machines, a Boltzmann machine is based on you training a probability distribution. And if you think of a Boltzmann distribution, some of you may be familiar with that, that has an exponential function. And the argument is normally, when you do statistical physics, It's the energy of the system. Now, this energy can actually be replaced by a neural network. And these Boltzmann machines are normally called energy models, and they have been extremely popular. You will often see that many of the basic types of modeling which we have in the natural sciences do enter the thinking in many of these neural networks or deep learning models. So typically a Boltzmann machine involves also training of the parameters and the network variables in terms of Monte Carlo simulations. And when you're modeling this, there are rules to update derivatives, etc. And you will encounter names like Langevin modeling. You will encounter stable diffusion as an algorithm, a very famous algorithm, which has been very important for the development of tools like ChatGPT. I should also say that we distinguish typically between discriminative and generative training or modeling. So discriminative is the one which we will deal with now. So we will take some input data, and then we have some output data, and we want to train a model to make predictions based on the data which we have trained on. So our main idea is to make a prediction based on either neural network, or we could even think of using something like standard linear regression, like the ordinary least squares method, which many of you may have encountered when you studied linear algebra. I'm assuming that most of you have taken a course in linear algebra, because machine learning at the heart of it is essentially linear algebra and statistics. These are the basic tools from these two fields of mathematics play a very important role in the development of our understanding of machine learning algorithms. So we have neural network types, and what we are going to focus on is something which is called feed-forward neural network. And I will try to expose to you the basic algorithm, and I'm going to put in some exercises which I will also refine a little bit later, so that you can take a look at these and see if you can get started with understanding the more complicated codes, because at the end of this Jupyter notebook, you will find an object-oriented code for a feed-forward neural network, which will allow you to study classification problems, but also to study a regression problem. So with regression, what we mean then is that we want to use a network to fit a continuous function which we don't know. So we have some input data, we have some output data which are labeled, and we assume that this data can be described by some function, which we don't know, and this function is going to be fit with a neural network. So that's a kind of basic overarching idea of every type of machine learning algorithm. Now, if you're taking a course in machine learning, one of the first approaches you will meet is something which is called linear regression or ordinary least squares, because then you have a simple problem where you can train the unknown parameters by simply performing a matrix inversion. And that is the standard ordinary least squares, which was invented by Gauss something like 200 years ago. You may ask why this is included in machine learning texts, because it's something which you would call a low-level type of machine learning, because you have analytical expressions for the unknown parameters. So we have convolutional neural networks, which are widely used in image recognition. We have recurrent neural networks. We have autoencoders. And then if we go to generative methods, where we are trying to make a probability distribution, then we would use something like Boltzmann machines or variational autoencoders. We can use GANs, generative adversarial neural networks. We have stable diffusion models, etc., etc. But we are going to focus on the multi-layer perceptron. And the way you can think of this is that you can, if you think of a simple perceptron, so the model is actually borrowed by the whole idea of a perceptron comes from neuroscience. And there is something which is called the universal approximation theorem, which states that a feed-forward neural network with just one single hidden layer containing a finite number of neurons, or nodes as we will also call them, that can approximate a continuous multi-dimensional function to an arbitrary accuracy. Now, so if you look at a simple perceptron model, this is actually a model which cannot fit a complex, continuous, multidimensional function, which is non-linear typically. And but it does a pretty good job in fitting a linear function. But here you see now the basic idea. You have some input. This input is now weighted with some parameters. This is fed into a function which produces an output. Now, this output, which we have here, is normally compared to some data. And the data are the output of a specific calculation we've done, or an experiment, or many, many other things which classify our data. A hidden neural network is then a neural network with hidden layers. So this system here has no hidden layer. Here we have an input layer where we feed in an input, and this input is fed into the hidden layers. And the hidden layers can have a complexity with many, many different nodes. We can have as many layers as we want, but then the training becomes complicated. And there is an output layer. So let me break down the speed a little bit and switch over to the whiteboard. So let's just switch over so that we can take a closer look at some of the basic ideas which we need to have in order to see the main picture here. So what we are having is, and now I'm writing this as a vector, so we can think of having some input data and some output data. And this output data, which is y, oops, sorry, just a moment here. This output is now given by some function of x, plus there can be some arbitrary noise here, which we are not going to say much about as of now. So this could be a continuous function. If we are dealing with a regression case where we want to fit a specific function. And we would typically call this the output. And these are data which we have. And this x would be the input. Now, in principle, we don't know this function f. So this is something which we want to fit. This can be some noise, which we could assume is normally distributed. Alternatively, this f of x could be a probability distribution. And this is very relevant if we're looking at classification problem, because if a probability is set up properly, it takes values between 0 and 1. And then you could say that if the probability is less than 0.5, then the output is 0. And if it's larger than 0.5, the output is 1. So that could be used for a binary classification problem. But let's try to stay with a continuous function, which we now want to fit. And a lot of machine learning deals with you making a fit to the data, and then you use this fit to make predictions. So what we make then is a model. So this model could be a polynomial, which we want to fit. So the model is something which I will call y tilde. And now we can break this down into the single component. So we have an observation, which is given by this function we don't know. So the quantities which we have are the xi's. These are the inputs. And then we have the outputs. And then we want to make a fit. And we can now make a model. So we have an epsilon of I. So this model could be a polynomial to a certain degree. So we could now assume that this has some parameter. Let's just call this a parameter beta 0, which is the intercept. And then we have a beta 1 times xi plus a beta 2 of xi squared, etc., up to the degree of p minus 1 of xi to p minus n. Now, this is the basic kind of idea which I want to convey, because we are now going to make a model where we want this model, and now we write it as a vector. We want this to approximate y. And then we need to assess, so basically in machine learning, what we need to do then is to assess whether this is a good model or a bad model. So how to assess if the model is good, if this is a good model. And there are many ways to do that. Model or not. Now, if you now look at this polynomial fit which we made, we can actually write this yi in a more compact form. So we could actually write this in terms of a sum over the x values. So we have a sum over the, let me see, there's a question in the chat here actually. So let me just see here. Okay, so I can put back this link again here. So this is the link where you find the lecture notes. I think that's the one you were asking for here. Okay. Now, if you now look at this model, we can now think of this written in a more specific way. So we can think of a matrix which now contains the variables x. So we have an x of I, which is the row. And then this is multiplied by beta of j. In our case, if we do a polynomial fit, so this runs over beta from j from 0 to p to minus 1. So if you think of a polynomial, this is something we would write out like a j of p minus 1. And then we have this variable xi to the power of j multiplied with the parameter beta of j. Now, this x can be written out as a matrix. So our model can then be written out in a more compact way as a matrix x times a vector beta. So this matrix x is normally in machine learning called the design matrix. And if you're doing a polynomial fit, this applies to a polynomial fit. You will have ones here for the intercept. These are ones. And then you will have x0 to the power of 1, x0 to the power of 2. And this goes all the way up to x0 to the power of p minus 1. And this continues now with x1, x1 squared. And then we continue to the last one, which is x of n minus 1 of p minus 1. So this x is a real matrix of dimensionality n, which is the number of data points, times p. And this quantity beta is then a vector of length p, and that contains all the unknown parameters which we need to find. Now, one thing which is done then in ordinary least squares is that the function which we use to assess the quality of the model is normally called the mean squared error. And that's the function which we are going to look at now in the examples which follow in order to set up a neural network. So this is the mean squared error. This is one of the simplest possible functions. And this is given by a mean squared, which now depends on the parameters beta. And I'm going to write this in terms of a function which I call C, which is called the cost function. And sometimes you will see this called the loss function. And this function is simply given by the sum over all the observations we have. And this runs from I equals 0 to n minus 1. I'm starting at 0 because arrays in Python start with 0. And then I have a y of I minus this y of I tilde squared. And I can rewrite that one in terms of I equals 0, n minus 1. And if I do a polynomial fit, this is going to be given by the sum here, where I now have a j equals 0 to p minus 1. And then I have my x of I to the power of j. This is just for the polynomial case. of beta j squared. And if I'm doing a linear fit, suppose now that my model y tilde of I is just given by beta 0 plus beta 1 times x of I, just that we are making a linear fit here, then this function becomes quite simple if we have a polynomial fit, because then this function, which we call c of beta, is simply given by 1 over n, and then I have a sum from I equals 0 to n minus 1, and then I have y of I minus, and then I have beta 0 minus beta 1 times x of I squared. This is my model, which I have here. This is my minus y of I tilde. Then what we want to do is to find the optimal parameters. And then we minimize this function with respect to beta 0. This is the gradient. And we want the gradient of beta 1 to be equal 0. And that gives us the equations in linear regression for ordinary least squares. This is a famous expression which was derived by Gauss, least squares. And then I can find now that the parameter beta is going to be given by the inverse of that matrix X. So this is the matrix X, which we call a design matrix or feature matrix, multiplied with this matrix, multiplied with the output. So everything here is known. So that means that also my model is now given by X times this beta. So beta hat here is now the optimal values. And these are the values which minimize the mean squared error. So essentially now, when we are moving to neural networks, if you keep this example in mind, this is an analytical expression. And you may say, why is this included in machine learning textbooks? Now, it is included in machine learning textbooks because you can think of this as a low-level machine learning in the sense that you're learning the parameters beta through this equation here, where you now have an analytical equation, and you can simply invert this matrix, if you can invert it, and then you multiply with a new matrix, and you multiply with a vector y. So I like to call this low-level machine learning, and linear regression, which is this specific type of equations which we get, is now given in terms of simple analytical expressions where you learn the optimal parameters which minimize this quantity which you have here. So this equation is now general because you can have more than just beta 0 and beta 1, but you can have many more parameters. Now, in this particular case, for this function, we also have a nice analytical expression for the gradients. But if we don't have that, we need to use what's called gradient descent methods to train the derivatives. Because at the end, we want the derivatives to be equal to 0. Now, if you now look back at what we had here, we made a model. So this is our model. And in this particular case, we just chose a polynomial fit as a model. Now, when we now move to neural networks, then the network is the model, the architecture of the network. So if we now replace this way of thinking of the way we've been training these parameters beta with a neural network, we are now going to replace this beta with a parameter which I will call theta, which is going to contain weights and biases. Now, these weights and biases, these are the parameters we are now going to train. That means that when I look at this cost function, so let's now look at the mean squared error, and we are going to train a neural network for a mean squared error. So the function now is just given by the same quantity we had before. So we have a 1 over n here, and then we have a sum over all the data which we have. So this could be data over a given number of patients. And then we have the output, y of I, This is the target value, the one we want to reproduce. And then we have a model here where we have a yi tilde. But now this model here, so this is squared, this model now, which we have, is going to be a function of these parameters theta. And how do we define these parameters? So a neural network can now be thought in the following way. So let's look at the scalar case. And this is the case which we are going to look at in the examples which are coming. And these cases are often given in terms of simple graphs. So think now of you having an input x. So you have only one input variable. Then we are feeding this in to a function. And this function has now some parameters. So this function has some parameters which I'm now going to just call W1 here. This is an unknown parameter. And I'm actually producing an input to a function, which I'm just leaving unspecified as a sigma. And you will later see that this is often used in terms of a sigmoid function, but it can be many other types of functions. And this depends on some input Z1. There is something which I will call a bias, which I'm going to call for B1. So this is called the bias. This parameter here is now the weight. This function here, sigma c, produces an output, which I'm going to label like this. So this is my y of I tilde. Well, let's just, since it's a scalar, we are just going to call this y of I, no, y tilde. So this is a case which we would call a simple perceptron model. There is only one node here that gets the input. So this Z1 is actually given by X multiplied with W1 plus a B1. Actually, this case here is a case where you can fit a straight line. So if you have a linear dependence on the input variables, this is a simple perceptron model, which we have here. This is a simple perceptron model with just a scalar input. Now this produces an output. Now this output is now fed into a new function, which is this cost function, which we call C here, which now depends on these parameters, theta. So in principle, this function which we have here is now not a set of parameter, a function of beta, but a function of this theta. So our network is now producing an output. This output is now fed into this function, and then we compare it with the values which we want to target. So this is the y here. And we are just looking at the scalar case. So this is not a neural network because it has no hidden layers, but it's normally called a simple perceptron model. Now, if you now want to be a little bit more ambitious, what you could think of is actually to make a hidden layer, but still have scalar input. So let's just do that. So let's add a hidden layer or a hidden node. So then what we would have is an x coming in. This goes into the first function, which I'm going to call sigma 1. It takes the same type of input, z1. There are parameters, unknown parameters w1 and b1 here. And these are the parameters we need to fit in order to make this, as you can see here, we have a set of variables which enter this function, and we want to fit these by calculating their gradients and do the same thing as we did here. So now we have two parameters, a weight and a bias. The bias is often chosen in the training to be a non-zero variable, because in case the bias is equal to 0, you may risk that the weight is 0, and then the training of a network would stop. So if you now look at the case with a hidden node, then this produces an output, and I'm going to label this output as an A1. And A1 is the output of a hidden layer. So this quantity which you see here now, we are going to frame this in like this. So this is now going to be a hidden layer, just one hidden node. So this produces an output, and this goes now into a new layer. But since I only have one hidden layer, what I'm producing now is an input to what is called an output layer. And now I have a new function, which is sigma2, and that takes an input z2. There is going to be, so this z2 is going to be given in terms of new variables of w2 multiplied with a1 plus a new bias b2. This produces an output, which I now going, instead of labeling this as a y tilde, I call this a2. So this is my output of the network. And this goes in, so let's just give it a little bit more space here. This goes into this function C, which also gets as input the target value y. So suddenly now we have parameters. And these parameters are now, these are the unknown parameters. They're given by W1, they're given by B1, W2, and B2. Now, one thing I want you to note as well is that these terms here, these sigmas, they are now parts of the model. So I'm going to put this in letters here because we're going back. So the architecture now of the network, that is equal to our model. So the number of hidden layers, the number of nodes, the number of output nodes. In our case, we have just one. The cost function, which we define here in order to assess the quality of the training which we do, is also part of the model. So what you see here, this type of way of structuring the data and the training is something which now leads to an architecture of a network. The first term here, this is called the input layer. So basically what you see now in its simplest form with a scalar input, you have only one node here that produces a scalar output from the hidden node, which then is fed into the output layer. And that produces an output A2 here, which then goes straight into the function we use to assess the quality of the model. Now, guys, feel free to ask questions here. Don't just let me talk on and on and on here. But I wanted now to go back a little bit to the slides. So I'm going to jump a little bit back and forth between slides and the whiteboard here. So there's a question in the chat here. Let's now see here. Okay, so there's a formulario de asistencia. Okay, that was an answer to the question here. Good. So let's go back to the Jupyter notebook and take a look at that one. So what you see here is just a general setup of this network. And if we scroll down here, besides these textbooks, and I forgot to mention them, there are actually some very good textbooks which you can look up. So the books with which I normally recommend is this one of Sebastian Rachka. And this contains lots of examples of, and chapter 11 there contains, so if you go to chapter 11, that contains an excellent description of how to write your own code for a neural network. And I think that your university library, if you subscribe to, I think your university library should have it. If you guys don't have it, I can put the PDF file into the GitHub address. So just let me know afterwards whether you can access that textbook, because that textbook is extremely useful, and it contains okay, so there's a good question here in the chat. Why, if the bias is set to 0, the neural network training could stop? So let me try to explain that, because you could, by accident, when you do the training, you could have all weights equal to 0. If all the weights are equal to 0, then the training of the parameters would stop, because a neural network is trained the following way, and we are coming to that. So there are 2 steps. One, you initialize all these weights and also these biases to random values. And then you give the input, and then you let the network propagate forward till it reaches the output layer. Now, this output may not be equal to the data you want to reproduce. So then there is a back propagation stage where you actually, through the calculation of the gradients here at every node, because you would need now the gradients for every layer here. And by doing this back propagation, you update the parameters. But you don't want the gradients to be 0. So what you want to be 0 is this final function, which now is given by the mean squared error, which measures the distance or the difference between your output and the values you want to target. So an iteration in a neural network training means that you have a feed forward where you start, in the first iteration, you start with random values, and then you go back and forth where you update the gradients. Now, if these parameters W by accident are 0, then you can risk that the training stops in the middle of the network. And you still may not have a mean squared error, which is as close to 0 as you want it to be. Now, if you guys want to read more, there are actually 2 nice online textbooks which you can find if you click to these links, where you can actually download more about the mathematics of deep learning. And I also recommend these textbooks here. So if we now look down, look a little bit more at what we have. So normally the training of a neural network, because you can have many hidden layers, contains a feed-forward stage, which takes a given input and produces a final output, which is then compared with the target values. And then there is a back propagation state or stage where the unknown parameters theta are updated through the optimization of their gradients. So one thing I wanted to say is that at the heart of all of machine learning, there is an optimization part. So we have encountered now the input and the output data, which are fixed by some experiment or some data you have access to. Then there is a model part where you decide what the model is. And then there is a function which you use to assess if the model is a bad one or a good one. And then you calculate the derivatives of that model, because that model will depend on the parameters data. So the architecture then typically consists of an input and output layer, where the input layer is defined by the inputs, and the output layer produces the model output y tilde, which is then compared with the target values. And then you have a given number of hidden layers and neurons, nodes, that's part of the model or architecture. And then in each node, you have an activation function, which receives an argument. And this activation function produces an output. These activation functions are normally the same for all the hidden layers, but they can change when you come to the output layer. Because in the output, you may want to have a binary case, which then produces just 1 or 0, true, false. And then you would use an activation function to say that, okay, if the value is below 0.5, I spit out 0. If it's higher, I give 1. So I see there's another question in the chat. So let me see now. thinking about a function of one variable, it is known that if you have n data, you can fit them perfectly with exactly. Is there any simple general data to? No, this is an excellent question actually, and the one by Manuel here in the chat, because if an ordinary polynomial fit does the best job, and a polynomial fit, as you saw from the beginning of the lecture, is simply given by a matrix inversion problem, and everybody can do that. If that gives the best fit, because you can do this in few seconds or even less on your computer, there is no point in training the same function with a neural network, which then can contain many more parameters to train. Because if you look at the structure here, if you think of what you see here, if you now have 100 nodes here and 100 nodes here, it means that there will be 100 times 100 weights to train. So suddenly you have 10,000 parameters just between the first hidden layer and the second hidden layer. If you train a polynomial with, say, fifth order, and if that does a perfect job, that is something you would actually be able to do very, very quickly, whereas the training of the neural network would take a lot of time. So coming back to your question, Manuel, this is about the mathematics of a neural network. So if you think of the optimization problem, what we have then is the universal approximation theorem, which states that you can train. So this was done by Sybenko back in 1989. Then what you can show is that you can train with the sigmoid function as an activation function. You can train a function f of x here as a function of the parameters, the weights. And then for a continuous and deterministic function, you can actually train a neural network with one hidden layer and obtain a result up to a given error epsilon. But this does not say anything about the number of nodes you need and the number of hidden layers. So coming back to your question, this is the universal approximation theorem does not give you a suggestion on how many parameters you need in the model architecture, unfortunately. So if you go back then to what we said, we will have activation functions, which then becomes part of the model. You will have, and this may differ from layer to layer. And the last layer, normally called the output layer, has an activation function, which is tailored to a specific problem. And finally, you have a cost function. Now, in the training here, if you now think back to this ordinary least squares where you had an analytical expression, in the training, we do not have analytical expression for these parameters. And that means that we need to use what's called gradient descent methods. Unfortunately, I will not have much time to discuss that. So if this is actually something which we can discuss when we meet in person in Cali. Alternatively, if you're interested, I can send you to my lecture notes on machine learning, which I'm going to put in the chat here during the break. So we're going to make a small break now soon, so I don't put you all to sleep, guys. But you have methods here which are very important, because when we do a gradient descent method, we introduce a new parameter, which is called the learning rate. And this learning rate is now something which we need to tune. And you can tune that with no insight about the gradients. If you're familiar with Newton's method, then Newton's method is actually a Taylor expansion of your cost function around the optimal value. If you stop at the order of the second derivative, you have a matrix, which is called a Hessian matrix, which contains the second derivative of the unknown parameters. And if you have a neural network and you use Newton's method, and a neural network will, let's say, 1 million parameters, the matrix to invert will be a 1 million times a 1 million matrix. And you don't want to do that. So you often replace the second derivative in the Taylor expansion with a parameter eta. And there's a question here, what factors influence the choice of activation function neural network, and how do they affect model performance? That's a very, very good question. And the choice of activation function becomes a parameter for you. And if you go into the literature, you will see there are tons of functions. Now, the choice is often dictated by what you see here, that you're going to calculate gradients, which will involve the derivative of the activation function. So you want something which is realistic, but at the same time, you want to have something which is going to be simple from a mathematical point. And since you're going to calculate gradients, you will also have derivatives of the activation function, which will enter in the gradient descent method. So that means that you often want to have something which can be rewritten in terms of simple functions like the sigmoid, which just contains an exponential, which is also cheap to use. And what people do is that they normally do the training with different types of activation functions. And then they pick the one which gives the best result. But also, you try to use activation functions which allow you to perform the calculations in a reasonable time. Clearly, if you're training large language models, then you have trillions of parameters, and then the training becomes very expensive, and the electricity bill is going to skyrocket. Actually, Google, so I'm living in Norway, so I'm teaching from Oslo now. Google got actually a local city in Norway to build a big factory to train many of these models. And that factory takes 5% of the country's electricity production. So when you're doing these trainings, you want something which is simple to train and at the same time is realistic. You would play around with many different activation functions. And that becomes part of the training and the architecture which we have defined here. And there is also something which I should add, is that the whole field was almost dying out because people used the sigmoid function to train a network back in before 2010. And the sigmoid function has something which is called vanishing gradients or exploding gradients, because it flattens out when you go to large values of the input argument. And when it flattens out, you get gradients, which are close to zero, and then the training stops. And then people replace the sigmoid function with other type of activation functions. And it's pretty common when you run calculations with neural networks to try different activation functions. So I hope that answered your question, Anna Isabel. Okay, so the approximation, the universal approximation theorem was modified by Hornick in 91, and then extended the theorem by letting any non-constant bounded activation function to be included. And however, as it says, the class of functions that can be approximate a continuous one. If it's discontinuous, it won't in general be possible to approximate it. However, an NN may still give an approximation, even if it fails in some points. So the by the way, the lecture notes which you have here, they contain essentially how to build a neural network code. But then my general lecture notes, which is a course which runs over a full semester, I'm going to put the notes in the chat here during the break. So the thing which I now wanted to do is actually to set up the equations for a neural network. So I want to step you through the basic ingredients. And we are going to use this as a cost function. And we are going to take the derivative of this function. And we are going to look at how we can do that with a scalar case. And then we can increase it to a case where we have a vector as input, and then more than just one hidden node, and more than one hidden layer. But I suggest that we take a small break now. Is that okay with everybody? Because I've been speaking for, I hope I haven't put you guys to sleep, actually.
No, I don't think so. So Morten, how much time do you think is okay for the break?
Is it 10 minutes okay for everybody? Then you can
Okay,
stretch
nice.
legs and grab a good cup of Colombian café. And un cafetitos necesito, eh?
Yeah.
And I'm going to put in the chat here the link to my machine learning course, which is also on GitHub, and you can just use it as you want. That contains also many, many different textbooks, which you can also download if you want to. I hope the pace was okay, and I hope it's not too boring. That I guess that you guys have seen many of these things before. And, okay, let us just stop sharing, and then we take a small break and be back in 10 minutes. Huh?
10 minutes, so we will be resuming 11:15. It's
Yeah, 11.
It's okay for you.
La
Gracias.
11:15.
Okay.
Perfecto.
Gracias.
Bueno, me voy a poner un vaso de agua. So bienvenido de nuevo. And if everybody's okay with it, we can start again if everybody's okay. Okay. So I'm going to bring up the slides again, which you should have access to. I also put in the chat the link to my general course on machine learning as a Jupyter book, and also the GitHub address where you can fetch all material or just download it to your laptops if you want to. So let me bring back the slides. And now we're going to be a little bit more ambitious. And we're going to see how we can set up the basic codes for a neural network. But I'm still going to stay with this simple example of a scalar input, or we are just going to extend this one to have 2 inputs, 2 hidden nodes, and 2 output nodes, or just 1 output node. But then if you see, when you see these examples, the hope is that that gives you the main overview of how you actually set up and train a neural network. So the basic algorithm is called the backpropagation algorithm, which is nothing but the chain rule applied to the derivatives of this function here. And now we are going to take a simple example where we now just train the so-called mean squared error. And I've taken away the number 1 over n, which is number of data, because in the scalar case, I'm also just going to have 1 output and 1 input. But in general, you will see this either written like this, because then you get rid of the factor of 2 when you take the derivative, or you will see it with 1 over n. But now we're just going to simplify things a little bit. So what I want to do now, before we move on, so the whole thing is that we want to calculate the derivatives of this function. There is something which will make life much, much easier. So I'm coming back to these things here. There is a very, very important algorithm. And if you have not heard of this, this is the time to look at it. And it's called automatic differentiation. The reason for why you should use this is that it makes life much, much simpler when you're training complicated neural networks with different functions. You want to play around with different activation functions. And in that case, you don't want to go into your program and hard code the derivatives of these functions. Also, it's a very important thing to keep in mind is that the backpropagation algorithm, which is used in the training of a neural network, is nothing but the application of the chain rule. And the example which I'm going to show you is an example which sometimes disappoints people, because you may ask, hey, is this backpropagation rule nothing but the chain rule? But I did this in high school when I looked at derivatives, right? So let me remind you of a little bit about the derivatives and partial derivatives and the chain rules, because we will often deal with gradients of functions. We will have to code everything as matrices, etc., etc. But automatic differentiation is the algorithm which breaks down the operations in terms of simple, because you often have simple mathematical functions for the activation functions and the cost function. And then you can break down the operations in terms of simple functions which define the derivatives. But here I just put in a multivariable function of x and y, where x also depends on t. And then we know that df dt is simply given by this expression here, where I actually leave out the explicit unit vector components. And that means that they will have an x derivative and a y derivative. And then if you have a multivariable function, a multivariate function, where also x depends on some further variables, t and s, then I would have to rewrite this one like that. Now, there is if you want to read more, there is actually a very good introduction in this article at Arxiv, which I highly recommend. So automatic differentiation is just represented by a repeated application of the chain rule on well-known functions, and allows for the calculations of derivatives to numerical precision. That is very important. It is not the same as the calculation of symbolic derivatives, Because if you use, let's say, Mathematica as an integrated development environment, or you use symbolic Python, what often happens then is that the functions which they produce are actually not very efficient from a computational point of view. And it's not based on the standard finite difference formula, because they are often error prone, and they will depend on truncation of the truncation errors and the value of the step size delta. So in the notes here, there are some simple examples which I just wanted to present to you. And clearly one very simple example is this one, and this is a derivative. Now, you would not code it like this because you would pre-calculate x squared, and you will see that in an example below here. But if you look at this function, you can actually rewrite it in terms of a equal x squared, and then you would have that f of x of a is equal to b, which is the same as exponential of a. So pre-calculating that one reduces the number of floating point operations. And it means also that you, when you calculate the derivative, you would actually calculate it in this way, where you have pre-calculated this one. Because if you now think of the cost functions, as you will see later, and also the activation functions, you will often calculate simultaneously the function f, but you will also calculate its derivative. And to recalculate that function like this and this is something which requires more floating point operations. And in Python, I can actually get out the expression for the derivative in terms of a Python code. And symbolic Python will give you this expression, which is not efficient enough from a computational point of view. Now, there's actually a little bit more here. If you look at this function, this function is something we would rewrite like this. So I want the derivative of f with respect to x, and I can start calculating the derivative at the endpoint and then go back to the beginning. This is called reverse mode. Alternatively, I can, if I now start with dA dx, I can have something which is called a forward mode. So I move from x to a, dB dA, and df dB. So you can calculate these derivatives in different ways. Now, a neural network training, if we now go back to that image which we had up here, if you look at the type of network which we can have, what happens often is that the output layer has less outputs than you have as inputs. Sometimes you just have one output for one set of inputs, which means that the output layer is often either represented by a scalar or by some quantity which has a lower dimensionality than the input. So starting calculating the derivative from the endpoint is often computationally more efficient than starting from the starting point. So essentially, when we are going to train all the parameters of the network, we are going to set up the chain rule. There is another example here on how you can actually make this more efficient. So if you scroll down a little bit, so this is the first one is called reverse mode. I start with dfdb, which is actually in our case just equal to 1, as you can see from the equations which we have here, because f is equal to b. And then I just need to calculate these two equations. This way starts with the dA dx, dB dA, and it's called the forward mode. So I start with the input values. There is a more complicated function, and if you now look at what I would get if I use SymPy, for instance, SymPy would produce this derivative here. And this derivative is a little bit more cumbersome, or requires more floating point operations. Actually, if you assume that every operation here takes the same time, then this operation which you see here is going to require 5 floating point operations. This is going to require 10. But what I can do then is actually to break this down in smaller functions. So I would have an a equal x squared, b equal to x exponential with a, c is just a plus b, and then d, which is equal to the function itself, is now equal to the square root. And then I can calculate, if I calculate the derivative by these steps here, what I get then is simply a derivative, which if we scroll down, so I invite you to take a look at these examples, which I can write in a very compact way. And since I have pre-calculated b and d when I calculate the function itself, then I have one addition, one multiplication, and one division. So that's three floating point operations if I pre-calculate the quantities. If you go back to the equation you see here, you would then have one addition, one multiplication, x squared, one exponential times one multiplication, so that's four floating point operations. Here I would have x times x, so that's one, and have one addition, another one, so two, and this one gives four, and then I have the square root, which gives me another operation, that's five. I have four in the numerator, and then I have a division, which is an additional operation. So in total here, I would get 10 floating point operations. Now, ideally, when I use automatic differentiation by calculating all these derivatives, there are additional operations. But automatic differentiation is normally based on, unless you can use simple analytical expressions, the final implementation of automatic differentiation involves repeated calculations of derivatives of elementary functions. So when you are setting up the activation functions, you often want these to be defined in terms of simpler mathematical or elementary functions. Now, I'm not going to go through everything here, but you can actually also, when you rewrite, so this, we don't have time to go through all the details, but I wanted now to show you the basics of training a neural network. So now we are going to simply have a case, which we discussed before the break, where we have a simple neural network, which looks like this. So we have an input, we have an unknown parameter, W1, an unknown bias. This produces an output, which I'm going to call for A. So this is my model. And this goes into the cost function. So that means that this cost function is now a function of this output, which is our model, the target value Y, and the parameters theta. So this means now that my cost function is now just given by one output, it's just a scalar, minus the target value which I want to reproduce. This is a function which it's easy to take the derivative of. A1 depends now, as you see from this function, it depends on W1 and B1. So if I now set up the gradients or the derivatives which I want to drive to zero, for this specific case, you see now that the chain rule gives me, if I use the chain rule, it gives me now the derivatives. And this dA dC1 here, which we have, is now the derivative of this quantity, which I call A1. And that is a function of the sigma z. So what I'm doing now is that A is equal to sigma z. So if I take the derivative of this one, so I'm just breaking this down, the parameter W1 is now given by simply this simple expression which you see here, and that is multiplied with the x value. So let's slow down the pace a little bit again and just take a look at this again at or using the whiteboard here. So let me just break this down and take a closer look at the calculation of this derivative. So let's look at this image which you see here, and let's just set up the derivatives, and we stop sharing. So if we now go back to this simpler model, which we actually had before the break. So before the break, we actually put up a neural network here, which is this one. So let's now just remind ourselves of what this looks like. So we are putting it back again. So we have an input value, x. This feeds into this function, which we now are going to call sigma 1 here. And that takes an input z1. And then I have a bias, a b1. It produces an output, which I'm going to call a1. This goes into the cost function, c, and it has a target value which we want to reproduce, which we also feed in. So this cost function is now just given by a scalar here. So it's a 1/2, and then I have my a1 minus y squared. Then what we have next is that we want to calculate the derivative of this function. So we want to have a d of c with respect to the w1. We want to drive that to 0, and we want to have a dc of b1, because these are the unknown parameters which we have. And we know that this function a1, which is given by this sigma 1 of c1, is the same as sigma 1 of x times w1 plus b1. So this is the functional dependence, and we haven't specified the sigma 1. A typical choice of this sigma 1 is to use the sigmoid function, which is given by 1 divided by 1 plus e minus c1. So this is a typical choice of activation function. You can have a tan hyperbolicus, or you can have other functions, which we will discuss later when we meet in person in Cali. Now, if you look at what we have now, is that this a1 is actually a function of x, of w1, and b1. So when we are now setting up the derivatives of these quantities, we are simply going to use the chain rule. And when we now look at the derivatives, what we are going to have is that dc of w1 is now going to be we are going to have a derivative with respect to a1, and then we are tracing ourselves through the derivatives, so we get the dc1, sorry, so we have a d of z1, and finally this is where we have the final dependence on w1. And you see now that if I take the cost function, I take the derivative with respect to a1, that gives me simply this term here, gives me a1 minus y, the target. This term here is now nothing but the derivative of this function with respect to c1. So we would write that one as the derivative of sigma 1. And finally, the last term, when you look at it, we have that this variable z1 is given by this quantity here. So if I take the derivative of that one with respect to w1, that gives me simply x times x. Then I have the derivative of db1, which is again, if we use a chain rule, of dA1, of dA1, of dC1, and then I have a dC1 of dB1. And this quantity is just equal to 1. If we just go back to the equation here, you see that C is given by X, W1 plus B1. And that gives us then a new expression here, where we collect these ones, where this is given by A1 minus Y times sigma 1 prime. And it's pretty common to just bring this together into one variable, which we call delta 1. Now, how does the training go? So the training is now done by Newton's method, or an approximation to Newton methods, which is gradient descent as a training method. Gradient descent to train gradients. And to train gradients means simply that we want to drive them to small values. And if you think back to Newton's equation, so Newton's method, if we want the roots of a function, so if we have a function f of x and we want that one to be 0, then the iterative scheme goes like this. We have an x after an iteration n plus 1. So you would start with a guess, which is x of n. You derive this result by performing a Taylor expansion around the optimal value. And then you keep terms only to second order in the derivatives. And this is given by minus f calculated at x of n divided by the derivative of x of n. Now, in our case, the function we want to drive to 0 is actually the gradient or the cost function. So that means that the function you see here has to be the second derivative of the cost function. So this is the gradient with, sorry, not beta, but theta. And so these are the gradients with respect to a parameter theta. And this is the quantity we want to drive to 0, which means that ideally the parameters theta of n plus 1, if you're using Newton's method directly, is going to be given by the second derivatives, which are called the Hessian matrix. And this has to be inverted. And this is a matrix which is complicated to derive. As I said before the break, if you have 10,000 parameters you're updating, this matrix will be a 10,000 times 10,000 second derivatives. And this is calculated at the value of theta of n. And then we have the gradient of c calculated at the same value of theta of n. Now, this quantity is replaced by what's called a learning rate, which becomes a parameter. So if you can improve one of these methods, this is actually something which can make a huge progress in the field, because you're doing these operations again and again and again and again. And actually, I used to say jokingly that this is a place where you guys will get many, many more friends. And I'm not inferring that you don't have friends, but these are friends which will cite you. So there's a popular method which is used to update this learning rate, which, as we call it, which is called ADAM, Adaptive Gradient with Momentum. And that paper came in 2014, and it has close to 200,000 citations nowadays. So this is a huge field in machine learning on how to calculate these gradients in the best possible way. So what we end up doing when we now have these gradients, these quantities here, what we want to do then is to use Newton's method to update the gradients. So that means that we will get a new W1 by calculating W1 minus this learning rate gamma, which we just leave unspecified. And then we have the gradient of DC W1. And then we update B1 by Newton's method or quasi-Newton methods or just plain gradient descent, where we now don't calculate the second derivative anymore. So these are the equations which we use in updating the values of the parameters. So these are the gradient descent algorithms. Now, for this specific case, which we looked at here, we have just one simple perceptron model. There is no hidden layer. Let's now just be a little bit more ambitious and go back to the Jupyter notebook and look at the case with a hidden layer. But still, we stay with a scalar input. So let's do that. And then you will be able to see the basic ingredients which are needed in order to set up a neural network code. So let's do that. So here, what we have done now is to set up the parameters, as you can see here. And in this specific case, we have a very simple algorithm which we can easily train. But let's add a hidden layer. So what we are doing now is to, if we now go down here, we have now modified what we had previously. So we have this term here is now the hidden layer, and that produces an output A1, and that feeds into an output layer, which is this one. And this variable C2 is given by W2 times the previous value, instead of X as we have here, plus a new bias B2. So we have, in total, we have 4 parameters we need to train. And our cost function, which we want to optimize, is this one. And this depends on W1, W2, B1, and B2. So when you have that, then what you see now is that the derivatives become a little bit more complicated. But you can now train this by using the results from the previous layers. And what you would do then is that you would calculate all these derivatives by simply using the chain. And you see now that here we have essentially the same type of equation which we had before, except that the activation function changes. It could be the same, but normally it's not the same on output layer. If you're dealing with a regression case where you just are fitting a specific function, it's common that the function sigma 2 here just spits out the value C2. If you're doing a classification problem, then you often want this sigma 2 to behave like a probability distribution, which spits out either 0 and 1, depending on a given threshold value. So if this sigma 2 is less than 0.5, for instance, it spits out 0. And if it's larger, it spits out 1. So the sigmoid function, which we saw previously, is a function which takes values between 0 and 1. So essentially, your algorithm is given by this. And if you go back now, the way you would set up your neural network is by first initializing these parameters, W1, B1, W2, and B2 with random variables. Then you perform the feed forward stage, where you take the input, produce A1, send that one into the next layer, produce A2, and then you compare that with this cost function. So the quantity you want to drive to 0 is actually this one. So when I now have produced an output, I have some specific values for W1, W2, etc., which were set randomly. And then I calculate these derivatives. And by the gradient descent method, I'm now updating the parameters with the gradients. So the gradients allow me to update W2, B2, W1, and B1. So this training part is important in the sense that I don't want to drive these derivatives to 0. The quantity I want to drive to 0 is actually this quantity. I want the mean squared error to be as small as possible. Ideally, it should be 0, because then I have a perfect fit. So if you then continue like this now, what we have now is a recipe for setting up the gradients. So one thing you see here is that the derivatives of these activation functions play a central role. If they vanish, then the training may stop. And this is called the vanishing gradient problem. And if they become too large, then these parameters may simply go to infinity. And this is normally called the exploding gradient problem. And this is something which we always have to deal with when we are training a neural network. So the training then is simply then done by you choosing, let's say, this parameter learning rate. And then you would simply go back and forth with a feed forward and a back propagation part, where you then simply train all these parameters here. And for the first hidden layer, the A0 here is actually equal to X for the simple model. So here is a simple equation, a simple program, which actually implements the back propagation algorithm, which is given by these derivatives. And these derivatives are now given in terms of, hopefully, simpler functions. And now you see also why it's important to have a function which has derivatives which are easy to calculate. And this is often done by using automatic differentiation here. I see there's a question in the chat here. Okay, now this is just a message to you all here. So let's take a look at how you can train this model here. And this gives you the essential elements of how you would set up a neural network code. But keep in mind that the input is just a scalar. Now, the program you see here is actually set up so you can send in a matrix X and also have vectors or more variables than just one. But in this specific case, I've tailored everything to just a scalar input. So I'm using the sigmoid as activation function. This is something you can change. In this case, I'm also not using automatic differentiation. If you scroll down in the slides here, you will find a full object-oriented code, which also uses automatic differentiation. So this is my sigmoid. This is my feed-forward part. So this is the C1 you see in the graph. And in this case, we don't need to do a matrix multiplication because we just have two variables. So this is X times W1 plus B1, which is what you see up here, this quantity here. That means that there is the next layer, which now depends on the output from the hidden layer. So you can see that A1 is the sigmoid of this argument, and C2 is now the argument which goes in. But since I'm going to fit a function, which is hopefully a continuous function, I'm just sending out A2 as C2. And this returns A1 and A2. So this is a forward propagation. So one iteration in a neural network calculation contains a feed-forward pass, and then there's a back propagation part. So let's just go back a little bit here. So what I'm saying now is that I want to fit this function here, and I want to, in my calculations now, what I'm going to print out is the cost function for every iteration. So my inputs now have only one feature, so it just scalars. There's one hidden neuron and there's one output. So I initialize my weights, keeping a kind of matrix vector notation, which I will come back to. So I have a random initializations. So this is a random numbers according to the normal distribution. And I put the bias to zeros plus a small number. And this is actually to start the training in case the random numbers here are very small and give derivatives which are close to zero. And then I have the weights and the biases for the output layer, which I initialize randomly. So what I do first now is that I have a number of iterations. So I do 50 times, I fix eta. The results will depend on eta here. And then I do 50 iterations. So that is one feed-forward pass and one back propagation pass. And in the back propagation, I calculate these derivatives. So the derivative of W2, W1, the bias 2, and the bias 1. So this back propagation, when I call it, is now calling the forward propagation part. And it produces A1 and A2. So if we go back to the graph here, I have a feed-forward pass, which now produces A1 and A2 with the initialization of the weights. Now, when I have that, I'm now computing this quantity delta 2, which if you go back to the equation here, is equal to this term you see here, that one. Then the next term which I need now, so I'm just actually printing out, this is my cost function. So I print it out for every iteration just to see how it diminishes. And then I calculate this term delta 1, and I'm using the sigmoid. So what I have done now is to hard code this quantity here, which is a derivative of the sigmoid function. So if we go up a little bit again, you see now that I am hard coding these derivatives of the sigmoid function, which then contain A1 times sigma 1. And this is actually the derivative of the sigmoid function, the sigmoid function, which I need here. This is the derivative of it. And then I have this delta 2 multiplied with W2. So if I then go back, I'm having the setup of this equation and also this equation here. And then finally, I do the final piece for the derivative respect to W1 and dB1, which I obtain by the chain rule. So everything we are doing is just a repeated operation with a chain rule. Now, these derivatives are derivatives which I am hard coding here, as you can see in this expression here. I have this delta 2, which I also hard code. And then I calculate the gradients. And then I calculate the gradients of the output bias and the output weights, and the hidden weights and the gradients. And these are the quantities which I now return, the gradients. And when I have the gradients, I do an update of W2, B2, W1, and B1, which are then given by this parameter eta, the learning rate, which is a parameter, which we have to tune in the training. So if I run this code, what you will see now is that my initial difference between, so this is the initial difference between, if we scroll up a little bit, this is the initial difference between A2 and Y. And you see now that this is a pretty large number. And then gradually, as we move on, this difference is 10 to the minus 8. And if you can accept a difference of 10 to the minus 8, then this is actually a pretty decent result for the cost function. Ideally, it should be equal to 0. Now, one thing you will see now is that everything depends on this parameter. So this becomes a parameter in the training. So if I make it smaller, it means that you will barely move. And if I have only 50 iterations, this may not be very efficient. And you can see now that if I make this very small, then the gradients are not changing very much. And you see that after 50 iterations, I have barely moved. If I make it too large, suppose I put it equal to 1, then I'm going to get values which also don't converge properly, and they actually get stuck here. So this becomes a parameter in all of machine learning, which we need to train. So this is at 0.1. When we did that, we can also change the function. There's nothing which hinders us now to use this function. So we could have a second order polynomial plus x times 5. Just to give an example, we haven't plugged in any noise. So let's see how this training is going. So you see in the beginning, with the random weights, the difference between the first output, because this is the first iteration, is not that good. And then as we keep moving, you see now that after some 50 iterations, we're actually getting a result which is pretty small. And we could then say that in this way, we have trained a neural network and gotten a very small value. Now, this training is, if you were to use ordinary least squares, this training wouldn't be very efficient because ordinary least squares would give you these coefficients 2, 1, no 5 here, and 1 by matrix inversion, and you would need only 3 parameters to do that. But what you see here is actually the basic approximation to a neural network. So I invite you, if you have some time and want to look at this, you could now add more data points, because remember now that I have only 1 point. So I'm just starting with the 1 input value and 1 output. You could now rewrite this one as a vector. And you could define x as a vector, because now I'm just putting x into a number as a number, right? That's my initial value for x. So there's only 1 scalar in and 1 scalar out. And one thing you could do now is to modify this program and simply train it with more input values and more output values. And you could also add things which are called hyperparameters, which are discussed a little bit later. And then you could also try to use automatic differentiation on these variables. So now you can increase the level of ambition, and we can look at a neural network with the 1 hidden layer, but 2 hidden nodes. And we have 2 input variables, which means that now suddenly this W, which we had, which was a scalar, becomes a matrix. So W is now represented by, for the hidden layer, it has a parameter. So this 1 here stands for the first hidden layer, and 2 here, which is now the output layer. This produces only one single output. This number 2, this superscript which you have here, now refers to the layer which we are having. So 0 here, which you see on the superscripts here, they refer to the 0th layer, which is normally called the input layer. And every layer will now have, this one will have its own parameter. So if you start counting, you have 4 weights, which are unknown, and 2 biases. So that's 6 parameters for the hidden layer. And then you have 2 weights for the output layer and 1 bias. So in total now, we are going to have 9 parameters which we need to train. So we need 9 derivatives. So 3 derivatives for the output layer and 6 derivatives for the hidden layer. And that means that when we are setting up things now, so we would have a total set of parameters, as you can count, as you can see here, there are 9 parameters which we need to set up. And these parameters refer to the figures, which means again that we can now rewrite this C0 in terms of a matrix times the input variables, which I label with a 0 superscript. This is x0 and x1, plus the bias. And sorry, and the outputs are now just given by the function here. And the final output layer has a variable C2, which is now given by these 3 parameters, which are unknown. And that results in an output here, which looks like that. And here, what I've done, and this is what I invite you to take a look at, I've set up all the derivatives which you need. And so I'm not going to go through that because I will leave that as a small homework for you guys. It's simply now to convince yourself about the correctness of the expressions. And that is going to give us derivatives now for the different parameters, which are going to look like this, where this delta 0 is now given by the derivative with respect to the input values times this delta 2 here. And then we have a whole chain of derivatives for the different layers. And that means that we also have a final expression for the biases of the hidden layers. And these are the parameters which I would need to train. So I have the weights for the output layer. So there are 2 weights. I have the biases for the output layer, which is just 1. And then I have 2 biases for the hidden layer. And I have 4 weights for the hidden layer. So what I would ask you to do now is actually, as a small exercise, take this example which you see up here, the one which we have here, where I've actually written things out in terms of matrices and vectors as well, except that we run everything for scalars because that sometimes it's easier to understand. And then take that one and try to implement that on this function, which is a 2-dimensional function, which now has an input with x's. So we have x0. I can have many values for x0. In our case, we just took a scalar. If we stay with that, if we have only 1 input variables, these ones, then I would just have x00 and x01. So the second column here refers to x1, and the first column refers to x0. And each one of these has 100 entries. So that means that you will get a structure which looks like this. And it just continues all the way down here. And so you see now that you go to the last point, this is n-2, n-1, and this is x0. And you similarly for x1, which has 100 entries. And you could try to write a code then, because with 100 entries, x0 and x1, you also have a specific output. So you would have 100 outputs. So each line here would then give you an output value y. So you could call this y0, which contains x00 and x01. And then you would have 100 inputs, sets of x0s and x1s, and 100 outputs. And then try to train that network with first thing you could do is actually just to have 2 hidden nodes, and then you would have 100 inputs here. Alternatively, you can just reduce the dimensionality of this input to contain just 2 inputs here. Now, to wrap up, if you then scroll down here, what you will find, if you scroll down, you will find the equations for a general neural network, which is the backpropagation, which is nothing but the chain rule in its reverse mode. And then, if you really scroll down here, you will now find how you can set up a code for yourself. There's first a code which is not object-oriented. And then if you scroll more down here, you will come to the full, so this is just an example of a classification problem, which you could go through till we meet again. And this goes through all the basic elements which are needed. I'm just scrolling quickly through here. But then you could then, when you get down, you can then find an example where we are setting up a network which now is a fully object-oriented network. So if we scroll down a little bit, so there's a code using scikit-learn. But at the end here, you will find an example on how you can build an object-oriented neural network code. And feel free to take a look at these codes, but also try to see if you can understand the basic steps which lead to the setup of a neural network. And if you have understood these basic steps, then you should know that a neural network is actually used often as a building block in convolutional neural networks, recurrent neural networks, autoencoders, and also in generative models like energy-based models, in many other deep learning methods. So I'm going to stop here. And I look very much forward to meet everybody in Cali. And I see that there's a question here. Maybe I missed something in the example. You change eta by hand and mentioned that the model should also be trained to choose an adequate eta. So this is the weak point of all this training. And this is a very good question, because what you would do is to play around with different values of eta. If you now look at the example codes which we have, so let's just go back to one of these example codes. If you just go up here, what you would typically do now is to choose a set of variables, eta, and in here we choose eta values which go from 10 to the minus 5 to 10 to the 1. I pick 7 values. I can also add so-called hyperparameters, and when you've done the training, then you would make a heat map, and then you would pick the result which gives you the best, for instance, mean squared value. So in machine learning, you can then also update this learning rate with different optimizers like this Adam I mentioned, or other methods. But the whole thing is that this is, as you point to, is actually one of the weak points of all machine learning methods, because unless you have analytical expressions like you had in ordinary least squares, you will always have to deal with the calculation of gradients, and you want to avoid calculating the second derivative of the function you optimize, because that is a ugly beast. So this is the less nice part, which often disappoints people when they look at deep learning, because suddenly there are many parameters which we have to tune. I hope that answered your question, Manuel. You do have a grid search for these parameters, and sometimes you also use a randomized search. The two most sensitive parameters are this learning rate in the gradients and something which is called a hyperparameter, which gives additional terms in the function you're optimizing, which we haven't discussed now. Feel free to use these programs as you want. Feel free to send me questions if there are problems, and don't hesitate to ask, please. And then I really look forward to meet all of you in Cali in is it 3 weeks now, Omar? Something like that? Yeah.
Yeah, 3 weeks, 3 weeks now.
Yeah. Bueno, gracias de todo, ¿eh? Gracias de la atención. Y a presto. Hablamos.
Well, thank you so much, Morten, for the teaching today. So everyone is free to keep doing the exercise, and then in 3 weeks. So thanks a lot in the face-to-face session. So thank you so much for being here, and have a nice day.
Ciao.
Thank you.
Bye bye.
Hasta luego.